Hello, everyone. I'm Zhou from Tsinghua University. I'm honored to present our work, NS4, enabling programmable data plane simulation. And the other authors also include Jiasong, Junbi, Peng, Kuang, Chengze, and Zhang. Let me start with a brief illustration on general procedures of network simulation. To simulate various network features, such as new routing protocols, scheduling algorithms, and advanced packet processing functions, we should create a simulation behavior model to implement these features in network simulators. The simulation behavior model is developed with languages and libraries provided by the network simulators. After that, we should design a simulation network and send testing traffic to verify the behavior model. If the behavior model doesn't pass the simulation, we have to update the network feature design and revise the behavior model accordingly. This life cycle constitutes the phase 1 of network simulation. If the behavior model passes the verification, we can go to the next phase. In the phase 1, we can get a desired behavior model for specific network features. Then in the phase 2, we should port the behavior model to real network devices, such as ASIC-based switch, NPU-based router, and FPGA-based NIC. Until now, there is no efficient approach to translate the behavior model to code of real devices. Thus, we have to manually rewrite the simulation behavior model. However, there are two drawbacks in the above phases. For the first phase, developing the behavior model is time-consuming and error-prone, and even worse, requiring intimate familiarity with the simulators, which tends to be a steep learning curve. For the second phase, tightly coupled with the specific simulator, behavior model is difficult to be ported to real-world networks. For example, to bring a network feature into reality, it's inevitable to translate simulation code in a general-purpose language like C++ into those in hardware description language like Verilog, or even circuit board design. This translation introduces both redundant work and potential bugs. Now let's turn to emulating and simulating P4 programs. P4 is built on an abstracted forwarding model. This model contains various reconfigurable elements, such as parsers, match action tables, and compound actions. This model can be implemented on various real network devices. Through the forwarding model, we can easily define the parsing graph, control flow, table configuration, and actions in a P4 program, and do not need to know the underlying implementation of these devices. Then P4 programs can be automatically compiled and configured into the devices. There are a lot of researching works on network emulators for P4, such as BMV2 plus Midnight and Crystal Night. These network emulators can faithfully mimic behaviors of real network devices, as network emulators need to put real network software or devices in a testing network. Its scale is limited by computation and memory resources. However, there are few researching efforts on network simulators that can predict behaviors of P4-enabled networks. Network simulators run as computer programs containing mathematical models and can easily simulate large-scale networks, so it's without resource concerns. And the traditional network simulators, such as NS4 and OPNet, do not simulate programmable data planes. So P4 programmers lack for a convenient simulation tool to verify their ideas. for large-scale P4-enabled networks. To this end, we propose NS4, a platform combining the traditional network simulator, NS3 and P4 to achieve following advantages. From the perspective of network simulation, NS4 exploits P4 to simplify the development of simulation behavior model. Then P4 programmers can focus on, then simulation programmers can focus on core logic of network features and develop P4 programs agnostic to simulator implementations. NS4 also bridges the gap between simulation and deployment, as P4 programs can be automatically compiled and deployed into real network devices. NS4 can also be a convenient researching tool for P4 programmers. P4 programmers can find it easy to verify their ideas in large-scale simulated networks with NS4. Now I will show the design overview of NS4. Firstly, we develop an NS4 net device class to integrate the P4 pipeline into the simulation data plane. The NS4 net device can receive packets from the channel manager, which takes the responsibility of packet transportation in NS4. We also implement a P4 configurator. The P4 configurator takes P4 programs as the input and can define the P4 pipeline in NS4 net device. In the control plane, we design 3 models: NS4 runtime, NS4 controller, and the statistic collector to facilitate developing control applications. NS4 controller can be programmed to reactively control P4 pipeline, while NS4 runtime can proactively populate table entries. And the statistic collector is responsible for gathering statistics from P4 pipeline. All the 3 models interact with the data plane through a P4 pipeline agent. We implement NS4 with 8,000 lines of code based on NS3 simulator, and we publish the code at GitHub. As for the evaluation, we tested NS4 on the commercial off-the-shelf servers, and we evaluate NS4 with 2 metrics. The first one is effectiveness of NS4 based on a case study. And the second one is development complexity to show that NS4 can simplify the behavior model development. Firstly, to illustrate the effectiveness of NS4, we use NS4 to simulate a typical P4 program, SilkRoad, as a case study. In cloud data centers, a lot of traffic comes with a virtual IP address and needs to be mapped to a pool of servers with direct IP addresses. The software load balancer running on servers takes the responsibility for keeping maps of virtual IP addresses and direct IP addresses, while SRB comes with a large performance overhead. SilkRoad enables load balancing to be performed at wire speed by offloading SRB to programmable and cheap ASIC with the help of P4. However, since the lack of a P4 simulator, it's not possible to evaluate the performance of SilkRoad in a data center network by simulating its behaviors until NS4. In this case study, we simulate NS4 and SRB in a fat tree topology as shown in this figure. In the experiments, we can see that NS4 could provide a variety of evaluation metrics. These metrics help programmers to comprehensively understand advantages and disadvantages of their designs in large-scale simulated networks. We compare SilkRoad with SRB in terms of packet processing delay, device throughput and flow completion time. We can see that SilkRoad largely outperforms SRB in this simulation. Then we evaluate the development complexity to show that NS4 can simplify the development of simulation behavior model. We respectively implement 4 test cases with increased number of network features. Thus, the behavior complexity increases one by one. For the test cases, we quantify the development complexity with the line of code. We can see from the table that NS4 can largely decrease the line of code through enabling operators to specify network features with P4. Let me conclude this presentation. NS4 is a simulation platform for programmable data planes. The key idea of NS4 is to combine the traditional network simulator with P4. Compared with NS3, NS4 enables programmers to develop a behavior model with P4, thus decouples behavior model with simulator implementations. So operators can develop the behavior model without the need of knowing simulator-specific libraries. Besides, with the advantages brought by P4, the P4-based behavior model can be easily deployed in real network devices without code rewriting. Furthermore, NS4 is also a convenient simulation tool for programmable data planes. And our future work includes strengthening NS4 code base to fully support elements of P4 and improving the execution efficiency of NS4 implementation. That's all. Thank you.
Thank you.